Welcome back to Geometry. We are in section 2 of chapter 12, arcs and chords. And so go ahead, pause, come back and check. What percent of 60 is 18? 18 over 60 is 30%. What number is 44% of 6? Again, 0.44 times 6 is 2.64. And the measure of angle WVX, that is 29% of 360 degrees, right? So 0.29 times 360 is 104.4 degrees. Today we will apply properties of arcs and properties of chords. So we will use these terms: central angle, arc, minor arc, major arc, semicircle, adjacent arcs, congruent arcs. So what angle has a vertex at the center of a circle? Yes, a central angle. And what is an unbroken part of a circle consisting of 2 points called endpoints and all the points on the circle between them? An arc. So here we have an arc AC. So I'm naming the arc using the endpoints A and C, and then we have in red all of the points between them on the circle, right? So that's arc AC. So we have different types of arcs. AC looks kind of small. This arc, right, is looking larger, right? And so we say that a minor arc is equal to the measure of its central angle, angle X. And a major arc, this is the major arc, is equal to 360 degrees minus the central angle. So it is all the points that are on the exterior part of the circle from the central angle. If the endpoints of an arc lie on a diameter, then the arc is a semicircle. We have arc EFG, and that is equal to 180 degrees, right? And EG, this other arc, is also a semicircle, also equal to 180 degrees. Minor arcs may be named by 2 points. Major arcs and semicircles should be named by 3. So this major arc is ADC. If I said simply arc AC, we would assume, we would know that I'm naming the minor arc, not the major arc. Okay? The circle graph here shows the types of grass planted in the yards of one neighborhood. Find the measure of arc KLF. So we're finding a major arc. And this major arc makes up the centipede grass, which is 65% of the circle graph. 65% of the entire 360 degrees. So we could say that the measure of KLF would be 360 minus the measure of KJF, this minor, or this central angle, right? And so we could find that by adding 20%, 8%, and 7%, we get 35%. So 35% of 360 gives us this minor arc, right, of 126 degrees, this angle of 126 degrees. And now when we subtract that from 360, we have our 234 degrees. That is the measure of the arc KLF. Could we have also found it by using 65% of 360? Yes, we could. Okay, so what arcs of the same circle intersect at exactly 1 point? They are called adjacent arcs. Recall adjacent angles. Remember they shared a ray? Well, adjacent arcs share an endpoint. So we have an arc addition postulate, which is much like a segment addition postulate. The measure of an arc formed by two adjacent arcs is the sum of the measures of the two arcs. So measure of arc AB plus measure of arc BC equals the measure of the entire arc ABC. Arc addition postulate. Sounds a little like Noah's Ark, doesn't it? Adding all those animals. Just kidding. Okay, let's use the arc addition postulate here. We want to find the measure of arc BD. BD. Okay, there's some interesting ways we can find this measure of arc BD. Okay, we basically need to find this angle BFC and CFD. So one of them should jump out at you really quickly. We have a diameter BE and a diameter AC. Those are intersecting lines. So which angle do we know quickly? That's right. We know that BFC is 97.4 because it is a vertical angle to angle AFE. All right, so we know this is 97.4. We just need to find this. What else can we find here? Well, BE is a diameter, and so this angle AFE plus AFB must equal what? That's right, 180. So we can find this angle by subtracting 97.4 from 180. Well, they did it a little differently, and I like what they did. They said, look at AC, the diameter. That diameter is 180 degrees as well, and it's made up of 97.4, 52, and the missing angle. So we simply add the two known angles, subtract that sum from 180, and we now know the small angle that we need, right? And that angle is 30.6 degrees. So we have 97.4 degrees plus 30.6 degrees, and we now know that by the arc addition postulate, the measure of arc BD, remember the measure of the arc is equal to the measure of the central angle that forms that arc, and it is 128 degrees. Can you find the measure of arc LJN? LJN. Pause, come back, and see if you're right. Well, we know that LJN is everything except for these two angles, or arc LN, right? And we see that LN is a combination of 40 plus 25, arc addition. That's 65 degrees. So we simply subtract 65 degrees from 360, and we know that this large major arc, LJN, is 295 degrees. And that's it for the first day. You may pause and begin your work. On day 2, come back and continue from here. Okay, this is day 2 of section 12.2, and we're going to start with looking at this diagram. Within a circle, or congruent circles, there's a name of two arcs that have the same measure. What do you think that is? And they are congruent arcs, a word you're really familiar with. So in this figure, arc ST is congruent to arc UV, which means that their angles are equal in measure. We have theorems related to congruent circles. In a given circle or in congruent circles, first we could say that congruent central angles will have congruent chords. Okay, so chord ED is congruent to chord BC. They're equal in measure. And we can also say that congruent chords have congruent arcs. So if I know I have congruent chords, I can also say something about these angles and their arcs as well. Finally, the third thing we can say is congruent arcs have congruent central angles. So that was the converse of the very first statement, right? If I have congruent central angles, I have congruent chords. Well, I guess it's the converse of the second one. If I have It's a combination, isn't it? If I have congruent chords, I have congruent arcs, and if I have congruent arcs, I have congruent angles. Okay. Let's apply congruent angles, arcs, and chords here. Segment TV is congruent to segment WS. TV is congruent to WS. So find the measure of arc WS. Well, if these segments, these chords, are congruent, then their arcs are congruent, right? And we can say that because congruent chords have congruent arcs. And therefore we can substitute the expression TV, the measure of TV is 9n minus 11, and the measure of SW is 7n plus 11. We're just substituting here. And now solve. So we subtract 7n, we add 11, and we end up with 2n equals 22. So what does n equal? That's right, n equals 11. So we're supposed to find the measure of arc WS. So what do we need to do now? Substitute 11. And when you do, we know that that arc equals 88 degrees. So what else equals 88 degrees? You got it, arc TV as well. Okay, in this example, you're just given a statement without a diagram. You could certainly draw it. Circle C is congruent to circle J. The measure of angle GCD is congruent to the measure of angle NJM. Okay, so find NM. So go ahead and draw this, see what you come up with, and come back and check. So you should have a circle C with G and D on the circle with an angle, whatever you chose to make that angle. It might look different than this, but it should look congruent to the angle in your second circle, circle J, where you should have N and M on the circle. These two angles need to look somewhat congruent, right? You don't have these dimensions. I just wanted to see that you could draw what is stated in the statement. And so find NM. We now need this information, so you need to add that N, right? And to find NM, we know that that chord NM is congruent to DG because these are congruent circles. And so we just simply substitute these two expressions, right? We know that their 14t minus 26 must equal 5t plus 1. Boy, I don't have that here. So when you solve, you end up with 9t equals 27, so t equals 3. So to find NM, we would substitute 3 and have a length of 16. If you haven't already, pause the video and set these expressions equal and solve so it makes sense to you. Okay? I don't have a smartboard on today, so it's tough for me to write on this computer. Let's move into the next theorems. These are really important theorems. You should know that in a circle, if a radius or diameter is perpendicular to a chord, then guess what? It bisects the chord and it bisects the arc. If it bisects the chord, it bisects the arc as well. So CD, that radius, is perpendicular to EF. It says it right here. So it is bisecting segment EF and arc EF. Also in a circle, the perpendicular bisector of a chord is either a radius or a diameter. So if you are given an image and you see a perpendicular bisector of a chord, you know you're dealing with a radius or a diameter. JK is a diameter of circle A. Okay, so let's use radii, and chords. Draw radius RN. There it is, boom. Draw it in. Notice that RM is perpendicular to NP. Perpendicular. So we now know something about NP. It has been bisected. And so has this arc, right? They're telling us the length of to that point of intersection is 8, and from there to M is 9. The whole radius is 17. So can you find RM? Well, we just said that RM, a radius of the circle R, is 17. Rn is also a radius. So what must its length be? 17. And so now we can find NP by just determining the length of this chord, right? And what do we have here? A beautiful right triangle. That is the awesome thing about a radius and the chord that it's perpendicular to. We have these little right triangles. So whatever you do, look for right triangles in your life. They are so awesome, right? We know this length is 17. That is what part of this little right triangle? That's right, it's the hypotenuse. We know that this leg is 8. Can we find the missing leg? Oh, yes, we can, right? So we can set it up, substitute, pause and find it. And when you do, you know that the length of that little S to N, or that point of intersection to N, is 15. So if this length is 15, then what is the length of the entire NP? Well, we know that this intersection S to P is also 15 because this chord was bisected. So 15 twice gives us 30. Isn't that cool? Very fun. So again, it's all about right triangles. Thank you, Pythagoras, right? Pause the video, come back, check your work. And to the nearest 10th, PL is 12.9. And there you go. Have a wonderful day. Good job.